In this video, we will learn about sigmatropic reactions, which are reactions in which a single sigma bond is broken and a new sigma bond is made. The way that we categorize sigmatropic reactions is by giving them a label of being x, y, in which the x and y refer to an indexing of where the new bond is relative to the original bond that was broken. What's going on is that the bond that's broken in the product is between atoms that are numbered 1 and 1, and then the new bond that's made is going to be between atoms x and y. This probably doesn't make very much sense, so let's look at a few examples. The first one is going to be a 3-3 rearrangement, which we will spend some time looking at a little bit later here. But just to start, we'll figure out how this numbering works and make sure our mechanisms make sense. So for the mechanism, I always kind of follow the sigma bond that's broken and go through my pericyclic transition state. And so I'm showing you here this transition state just to remind us that this is what the transition state looks like. So kind of these half broken, half formed bonds everywhere. And in the product, these are the relevant pairs of electrons. Now let's look at the numbering that's used to come up with 3-3 here. So again, what I care about is that I'm going from bond broken to bond made, which would be bond broken, bond made in the second kind of copy of that reaction there. For my numbering then, I'm going to go to the bond that's broken. That's going to be my 1 in red and my 1 in blue there. So those two carbons are my 1 and 1. From there, I'm going to say that, well, I've got a number all the way out to these two N carbons right here, because that's where my new bond is being made. And so my numbering goes like so, 1, 2, 3 in red, 1, 2, 3 in blue. And so then, in my new bond, I have a 3 location for that new bond. That's why I call this a 3-3 rearrangement. Here's a second example. So this one now is a 1,5 hydride shift. In this case, a hydride, so an H and a pair of electrons, appear to be shifting around in the molecule. So from a mechanistic point of view, what we're doing is we're taking that pair of electrons. So I always personally think of that sigma bond as the pair of electrons is kind of shifting around. That's going to end up here, pushing the other two pi bonds around, getting you to this product. So the transition state for this reaction then is going to have kind of a transition state structure where that hydrogen, really that hydride, is kind of equidistant from the two carbons. So the first carbon from where it's leaving and the second carbon where it's now bonding to in the product. And you should get kind of this is not quite a triangle, but this triangular looking arrangement between those two carbons and that hydrogen. For the numbering then, again, we're going to keep track of where our bonds are broken and made. So this is the bond that's broken, and that is the bond that's made. There's no specific reason that the hydrogen has to be blue or red, but I'm doing red here just to be consistent. So the hydrogen will be the 1, and the carbon will be the 1 as well on my bond that's broken. And then, if I go to my product side here, well, the hydrogen is actually still part of the new sigma bond that's made. So that's still going to be the red 1. For the carbon side of this new bond that's made, however, that's no longer the same carbon, so I need to number and figure all of that out. So I'm going to go around following the pi system, and I see that I go 1, 2, 3, 4, 5. Again, I can't go the shorter direction here because that's not the pi system that's reacting, or there's no pi system there actually. So I need to go through in my reacting atoms in my numbering. So 1, 2, 3, 4, 5. That then gets me to a 1,5 hydride shift. So the question will often come up, well, why do I put the 1 first? Should I put the 5 first? The convention is to put the smaller number first. That's the only reason that the 1 came first. As you should be used to now, all of these pericyclic reactions have Woodward-Hoffman selection rules, and so sigmatropic reactions do as well. Again, they're going to follow the same type of pattern of going by the number of electrons involved in the process and then judging some sort of symmetry involved in the pi molecular orbitals, or I guess all the molecular orbitals that are reacting. So if you have 4n plus 2 electrons in your process, under thermal conditions you would want to do that suprafacial plus suprafacial, or technically anterofacial plus anterofacial. And if you want to do it photochemically, you would have to do a suprafacial plus anterofacial process. And the converse of all that is going to be the case for when you have 4n electrons in your process. Let's start off by looking at a 1,5-hydride shift on a slightly different molecule than the one on the end of the previous slide. So here we're looking at this molecule kind of oriented exactly how I've done my drawing, and I've highlighted in blue the hydrogen that is shifting, or the hydride that is shifting. And so if we follow through this animation of the reaction, we should be able to see very nicely that as we kind of go through this reaction, that hydride does kind of shift over, and at some point you get to this transition state where both of those carbons are equally bonded to that hydrogen, or I should say maybe half bonded to that hydrogen. You'll notice in my model that the carbon-carbon bond actually disappeared. The visualization of a carbon-carbon bond is just defined by the distance between the carbons. So what this tells you is that in this transition state, the atoms all kind of separate away from each other a little bit, to the point that the modeling software doesn't even think there's a bond between the two carbons. But this is the transition state and not an intermediate that can be isolated or anything like that. And so as soon as you're at the transition state and you go downhill in energy, then you get to the rearranged product like so. So if you're looking at this reaction, I think you can appreciate, let's go backwards here, that the hydrogen is remaining on a single face of the pi system. Right? That hydride is not kind of bouncing to the other side of the ring. It's staying above the ring as we're viewing it and just kind of shifting over to the side. And so it gives you a little bit of insight that that should be a suprafacial process with respect to the pi system. Let's look at the drawings for these orbitals now. This is going to be different from cycloadditions because we have a sigma bond involved. So what we'll do is to think of the HOMO of the group that's shifting and the LUMO of the other pi system. So if we look at that, then what we have is the diene is the LUMO, so just these 4 atoms here, part of a 4-atom pi system. That's my LUMO. And the HOMO is going to be the hydrogen's 1s orbital, because that's the occupied pair that's part of that sigma bond. And so just to be clear, I'm referring to that carbon-hydrogen bond here. So that's this bond way out here. And so that is made up by a hydrogen 1s overlapping with a carbon sp3 orbital. So when we're thinking about that, what we do is then to understand that an ideal way to set this up is to have the phasings here lined up with the end of our pi system, because that allows for some positive overlap. And so we would expect that the H1s should be the same phase as the sp3 end here, which is the same phase as the end of our diene LUMO. Our reaction is going to happen like so, where the H1s is essentially kind of moving over to this side, getting us to our product. And so if I show you the actual product here, you should get a system of orbitals that looks like this, where the H1s is there in blue. And now I've had a new 4-atom 2-pi system created right here. So if we're trying to categorize the kind of facialness of this reaction, again, the pi system is reacting suprafacially because we're staying on the same kind of above side of that ring. And the H1s orbital, well, it doesn't have any other phase than the single phase that the s orbital is, so we consider that to also be a suprafacial process. There's no change in phasing at which the orbital that's involved is mixing. So a 1,5 hydride shift is a suprafacial plus suprafacial process, and so we would expect that to take place under thermal conditions, given that this is a 6-electron process. This can often be confusing for students because they see the 2 pi bonds in the reactant and the product and think that there's only 4 electrons total, but we have to remember that there's a pair of electrons in that sigma bond as well. So this is indeed a 6-electron sigmatropic reaction. Turns out that while 1,5 hydride shifts are thermally allowed, 1,3 hydride shifts are thermally impossible. This is kind of an interesting phenomenon, but it all comes down to an analysis of the frontier molecular orbitals. So here's an example of a hypothetical 1,3 hydride shift where I would be arguing that, well, why can't I just do this? And, on paper that looks great. Everything actually works out distance-wise. A hydride would be able to, in terms of geometry, get over there, it seems. But if you do the orbital analysis, what you find is that the setup looks like this. So we have the LUMO of the pi system, which is 2 atoms now with 1 pi bond. So that would look like these two oppositely phased systems. Our CH bond that we're shifting would look like this, where we're setting up the phasing again to match that terminal end here. And if I'm trying to get this shift to happen, well, if I try to go suprafacial to the LUMO there, I can't really do it because the phasing isn't right. So I would need this H1S to go kind of around the other way to do this reaction. And so what's happening here is that under thermal conditions, I have to do a suprafacial plus anterofacial process. And there's no way for me to be anterofacial on a 1s orbital. So that means I have to be anterofacial on the other reacting piece here. And geometrically, that's just not possible. I can't have a hydride below a pi bond somehow flipping to be above. It would have to completely detach and then come around, which would not be a pericyclic process anymore, but rather an ionic reaction. So again, under thermal conditions, you will not get a 1,3 hydride shift. Under photochemical conditions, you could get a 1,3 hydride shift. This is interesting to compare to a different group undergoing a 1,3 shift, and it turns out that a thermal 1,3 methyl shift is possible. And so at first glance, you might think, well, you just told me that a 1,3 hydride shift isn't possible. What makes a 1,3 methyl shift possible? And the big thing is that we can get one of the components of the reaction to be anterofacial. So let's look at these orbitals. We're going to have the exact same LUMO for the, I guess, the ethylene pi system. But for the HOMO now, I have a sigma bond that is composed of an overlap between the methyl sp3 atomic orbital in our valence bond theory and the black sp3 orbital from the carbon up here. What this means is that I'm still probably not going to be able to have this group kind of jump to the other side somehow. So that makes me think I'm going to do my reaction suprafacially on the pi system here. And according to the Woodward-Hoffman rules, then I would have to be anterofacial on the methyl group. This is possible because I can imagine a process like this one, where my methyl is kind of flipping over like that, and that's enough of a mixing on the suprafacial side with respect to the LUMO to get this process to go. And so I have the transition state drawn out here, looks like that, where I am getting the correct amount of mixing that's going on there. And as part of that kind of total inversion, then my product will look like this from the MO perspective. So I think this is a really great example where just learning the rules doesn't get you quite to the conclusion that you need, but rather understanding some of the fundamental ways that this all works can really help out. Interestingly, if you take a 1,3 methyl shift, you should be able to figure out how this works under photochemical conditions and how that would actually take place under a suprafacial to plus suprafacial type of a process. The last type of molecular orbital analysis I want to go over is the hydride shift that takes place in carbocations that take less stable carbocations and convert them into more stable carbocations. So an example is here where we're going from a secondary carbocation to a tertiary carbocation. And so we learn this as just something that happens, but now we have the orbital understanding to understand how it happens. So same type of deal. We're dealing now with a pi system, which is really just this empty orbital right here. So we don't have a pi bond, but it's sort of our pi MO. So one orbital. And we have our HOMO, which is the H1S. Overall, we should see that we have a 2-electron system here. And in a 2-electron system, that's going to be your 4n plus 2 type of a category. So under thermal conditions, this would be a required suprafacial plus suprafacial process. And so you can kind of see how that's very easy for us to do. So you get the kind of 3-membered ring transition state, eventually getting over to product have the shift. So my point here is just that you actually had learned about sigmatropic rearrangements many times before, but now you've been given a name for it. This is a 1,2 sigmatropic rearrangement. I had mentioned at the very beginning of this video that there are 3,3 rearrangements, and that these are something we'll look more into. Turns out these are very common. Part of the reason is because these go through 6-membered ring transition states that look aromatic, and anything dealing with 6-membered rings and things that look aromatic are just very favorable type of processes. We're going to look at 3 different 3,3 rearrangements, and they all have a name attached to them. So the first one is the Cope rearrangement, and In a 3,3 rearrangement, the general pattern is that a 1,5 diene converts into another 1,5 diene. So the Cope rearrangement has our 1,5 diene. So 1, 2, 3, 4, 5. Undergoing that 3,3 rearrangement, like so. This apparently takes place at 300 degrees, getting us to another and different product here. The Cope rearrangement is a great way for building carbon-carbon bonds because it doesn't require any other functional groups out here, like no other heteroatoms needed, to get a new bond to be formed between these two locations. The next 3,3 rearrangement we'll look at is the Claisen rearrangement. The name is a little bit confusing because there is a Claisen condensation that was discovered by the same person, Claisen, but this is a different reaction because this is a pericyclic reaction. In this reaction, we're taking an allyl vinyl ether, so allyl referring to the ether's location on this group here, and vinyl referring to the ether's location relative to the alkene here, and we're transforming that into what's called a gamma delta unsaturated carbonyl compound, usually an aldehyde or ketone. So I've given you the Greek lettering here to explain why it's gamma and delta. This is a nice reaction because it's a way to install a new carbonyl somewhere different in the molecule. One interesting use of this reaction is the one that's shown here. So if we take an aromatic vinyl ether and we subject it to Claisen rearrangement conditions, so some heat, then what you end up getting is this phenol right here. And so this is a good mechanism to work through to see if you can figure out how overall this happened. So it's not going to be a single step. There's going to be something that happens after the initial 3,3 rearrangement. The last reaction that we'll look at is the oxy-Cope rearrangement. And you can kind of see how this reaction was developed if you imagine Cope and other scientists developing the Cope rearrangement, kind of thinking, well, what if I just have an alcohol here just to see if the Cope rearrangement works or not? And it turns out that it does work, but something else happens because as part of the Cope rearrangement, we create an enol, which we know should tautomerize into the keto form. And so this is actually a pretty cool way of transforming an allyl alcohol into a carbonyl. And so a lot of these reactions, we're not seeing the specific use case for these reactions, but there are just many different circumstances in synthesis where you require, in kind of a 6-atom type of a pattern, a carbonyl here and a pi bond out here. Or you might require the other way around, so the two alkenes in this 1,5 diene arrangement. And this is where these types of rearrangements will be very powerful for converting one type of structure to another. So that was a look at sigmatropic reactions. We went over the selection rules and the molecular orbital analysis that gives us some insight into how exactly these reactions happen. We didn't specifically talk about any stereochemical impacts, but if you go back and look at the 1,3-methyl shift, I think you can see how that methyl is forced to invert. So there could be stereochemical impacts given certain types of setups and structures. Finally, we looked at a few of these 3,3 rearrangements specifically and the types of processes they undergo.